Greetings. Today we will be talking about Lecture 2, Earth's Physical Systems, Matter, Energy, and Geology. This chapter will help students explain the fundamentals of matter and chemistry and apply them to real-world solutions, differentiate among forms of energy, and explain the basics of energy flow, distinguish photosynthesis, cellular respiration, and chemosynthesis, and summarize their importance to living things. Explain how plate tectonics and the rock cycle shape the landscape around us and the earth beneath our feet. And lastly, list major types of geologic hazards and describe ways to mitigate their impacts. We want to start off with a central case study, the Tohoku earthquake, as it shaken the Earth's trust in nuclear power. Little did anyone know that this quake would initiate a series of events that would not only affect Japan, but also the future of nuclear power around the world. The damage from the earthquake was supplemented by a following tsunami. A tsunami is a powerful surge of seawater generated when an offshore earthquake displaces large volumes of rock and sediment on the ocean bottom, slowly pushing the overlying ocean water upwards. The raging water swept up to 9.6 kilometers inland, scoured buildings from their foundations, inundated towns, villages, and productive agricultural land. The tsunami severely damaged the Fukushima Daiichi nuclear power plant. Engineers and soldiers risked their lives amid radiation to avoid a full-blown catastrophe. A 20-kilometer area around the Fukushima Daiichi plant has been permanently evacuated, and the full extent of nuclear contamination is still being determined. Full recovery from these events is expected to take decades. One of the longest-lasting legacies of these events may be the impact on the future of nuclear power in Japan and around the world. The Japanese government has championed a view that nuclear power was perfectly safe, but events at Fukushima have shaken public support for nuclear power in Japan. In North America and Europe, the events at Fukushima Daiichi caused the public already skeptical of the safety of nuclear power to become further wary of its use. Matter, chemistry, and the environment. An understanding of matter itself helps us to fully appreciate all the processes of our world. All material in the universe that has mass and occupies space is called matter. Types of matter and some of the important ways they interact are called chemistry. Matter is conserved. Matter may be transformed from one type of substance into others, but it cannot be created or destroyed. This principle is referred to as the law of conservation of matter. The amount of matter stays constant as it is recycled in nutrient cycles and ecosystems. Pollution and waste will not simply disappear when we dispose of it. Atoms and elements are the chemical building blocks. The nuclear reactor at Fukushima used uranium to power its reactors, and uranium is an example of an element. An element is a fundamental type of matter, a chemical substance with a given set of properties that cannot be broken down into substances with other properties. Elements especially abundant on our planet include hydrogen, oxygen, silicon, nitrogen, and carbon. The periodic table of the elements organizes the elements according to their chemical properties and behaviors. Atoms are the smallest units that maintain the chemical properties of the element. Atoms of each element hold a defined number of protons in the atom's nucleus, and this number is often called the element's atomic number. Most atoms also contain neutrons in their nuclei, and an element's mass number denotes the combined number of protons and neutrons in the atom. Lastly, an atom's nucleus is surrounded by negatively charged particles known as electrons, which balance the positive charge of the protons. In this slide, we can see common elements along with their respective number of neutrons, protons, and electrons. Isotopes. Atoms of the same element with differing numbers of neutrons are referred to as isotopes. Ions. Atoms may gain or lose electrons, thereby becoming ions. Electrically charged atoms or combinations of atoms. In this slide, we have an example of a possible hydrogen isotope and also a possible hydrogen ion. Some isotopes, called radioisotopes, are radioactive and decay by changing their chemical identity as they shed subatomic particles and emit high-energy radiation. The greatest danger from radioisotopes occurs when they enter the bodies of organisms through the lungs, skin, or digestive system. damaging radiation emitted by radioisotopes is called ionizing radiation because it generates ions when it strikes molecules. Each radioisotope decays at a rate determined by that isotope's half-life, the amount of time it takes for one-half of the atoms to give off radiation and decay. Molecules and compounds. Atoms bond together and form molecules, combinations of two or more atoms. A molecule composed of atoms of two or more differing elements is called a compound. One compound is water, which is two hydrogen atoms bonded to an oxygen atom. Another example is carbon dioxide, consisting of one carbon atom bonded to two oxygen atoms. Atoms bond together because of an attraction for one another's electrons. Some of these bonds are equal and others are not. When electrons are shared between atoms, a covalent bond forms. In compounds in which strength of attraction is sufficiently unequal, the electron may be transferred from one molecule to another. This creates oppositely charged ions that form ionic bonds. Elements, molecules, and compounds can also come together in mixtures without chemically bonding or reacting. Homogeneous mixtures are called solutions. Air in the atmosphere is a solution of many constituents, including nitrogen, oxygen, water vapor, carbon dioxide, methane, and ozone. Water's chemistry facilitates life. Water has unique properties that give it an amazing capacity to support life. When an arrangement allows water molecules to adhere to one another in a type of weakly attracted interaction, this is called a hydrogen bond. Hydrogen bonding gives water properties such as cohesion, high heat absorption capacity, a solid form that is less dense than the liquid form, and an ability to dissolve or hold in solution many other molecules, particularly ions and other partially charged molecules. As we can see here, and as we all know, ice is the solid form of water and it floats on the liquid form. Hydrogen ions also determine acidity. In aqueous solutions, a small number of water molecules split apart, each forming a hydrogen ion and a hydroxide ion, H plus and OH negative, respectively. Solutions in which the H plus concentration is greater than the OH negative concentration are acidic. The reverse case creates solutions that are basic or alkaline. The pH scale quantifies the acidity or alkalinity of solutions. pHs of less than 7 indicate an acidic solution. pH greater than 7 indicates an alkaline solution. Pure water has a pH of 7. The pH scale is logarithmic. Each step represents a tenfold difference in hydrogen ion concentration. Most biological systems have a pH between 6 and 8. As we can see, pure water has a pH of 7. It has an equal number of hydrogen and hydroxide ions. Matter is composed of organic and inorganic compounds. Organic compounds consist of carbon atoms joined by covalent bonds along with other elements, for the most part. One class of organic compounds that is important in environmental science is the hydrocarbons, which contain only atoms of carbon and hydrogen. The lightest hydrocarbons containing 4 or fewer carbon atoms are gases. Larger hydrocarbons are liquids. Those having more than 20 are usually solids. Some hydrocarbons form petroleum are known to pose health and hazards to wildlife and people. Some hydrocarbons formed petroleum have become ubiquitous in our modern lifestyle because they are moldable into nearly any shape and resist chemical breakdown. While these plastics have many benefits for manufactured goods, they can be a persistent source of pollution due to their longevity in the environment. Here we have various hydrocarbons of note. Notice they only contain carbons and hydrogens. Macromolecules are building blocks of life. Organic compounds sometimes combine to form long chains of repeated molecules. These chains are called polymers, and there are 3 types that are essential to life: proteins, nucleic acids, and carbohydrates, along with lipids, which are not polymers but are still classified as macromolecules because of their large sizes. Lipids include fats and oils for energy storage, phospholipids for cell membranes, waxes for structure, and steroids for hormone production. Although chemically diverse, these compounds are grouped together because they do not dissolve in water. Proteins consist of large chains of organic molecules called amino acids. They serve many different functions in living cells, providing structural support, energy storage, and immune system functions. They also act as chemical messengers as hormones and chemical reaction catalysts as enzymes. Nucleic acids direct the production of proteins. Deoxyribonucleic acid and ribonucleic acid, DNA and RNA respectively, carry the hereditary information for organisms. Nucleic acids are composed of nucleotides, each of which contain a sugar molecule, a phosphate group, and a nitrogenous base. Regions of DNA that code for specific functions are called genes. As you can see here, each nucleotide contains a phosphate group, a sugar, and a nitrogenous base. Carbohydrates include simple sugars that are 3 to 7 carbon atoms long. Among these is glucose, which fuels living cells and serves as the base for complex carbohydrates. Complex carbohydrates include starch, an energy storage compound, chitin, a structural component, shells, and cellulose, the most abundant organic compound on Earth, found in the cell walls of plants. The cells of eukaryotes, plants, animals, fungi, and protists contain a membrane-enclosed nucleus and various membrane-enclosed organelles that provide specific functions. Prokaryotes, bacteria, and archaea are generally single-celled, and their cells lack membrane-enclosed organelles and a nucleus. An introduction to energy. Energy is the capacity to change the position, physical composition, or temperature of matter. In other words, a force that can accomplish work. Energy comes in different forms. Two major forms of energy that scientists commonly distinguish are potential energy, the energy of position, and kinetic energy, the energy of motion. Chemical energy is a special type of potential energy that is held in the bonds between atoms. Converting a molecule with high energy bonds into molecules with low energy bonds release energy by changing potential energy into kinetic energy. Nuclear energy, another type of energy, holds the atomic nuclei together, and mechanical energy, such as that stored in a compressed spring, are also potential energies. In this picture, we see the energy of position, or potential energy, that can be converted to the energy of motion, or kinetic energy. Energy is always conserved, but it changes in quality. The first law of thermodynamics states that energy can be changed from one form to another, but it cannot be created nor destroyed. The second law of thermodynamics states that energy tends to change from a more ordered state to a less ordered state, as long as no force counteracts this tendency. Systems tend to move towards increasing disorder, or entropy. The order of an object or system can be increased through the input of additional energy from outside the system. In this example, we can see the potential energy stored in the molecular bonds of wood transformed into kinetic energy, which is released as heat and light, and in the end, we can see an increase in disorder or entropy. Some energy sources are easier to harness than others. The nature of an energy source determines how easily people can harness it. In each attempt we make to harness energy, some portion escapes. We express our degree of success in capturing energy in terms of the energy conversion efficiency, or the ratio of the useful output of energy to the amount we need to input. Light energy from the sun powers most living systems. The energy that powers the Earth's biological systems comes primarily from the sun. Some organisms use the sun's radiation directly to produce their own food. Such organisms are called autotrophs, or primary producers, and they include green plants, algae, and cyanobacteria. Autotrophs turn light energy from the sun into chemical energy in a process called photosynthesis. In photosynthesis, sunlight powers a series of chemical reactions that converts water and carbon dioxide into sugars, transforming diffuse energy from the sun into concentrated energy the organism can use. Photosynthesis produces food for plants and animals. Photosynthesis occurs within cell organelles called chloroplasts, where the light-absorbing pigment chlorophyll uses solar energy to initiate a series of solar reactions. In a series of chemical reactions called light reactions, photosynthesis uses solar energy to split water molecules to form hydrogen ions and oxygen that we breathe. The light reactions produce energy molecules that fuel reactions in the Calvin cycle, where sugars are formed. The net process of photosynthesis is defined by the chemical equation seen here. Animals depend on the sugar and oxygen from photosynthesis. Cellular respiration releases chemical energy. Organisms make use of the chemical energy created by photosynthesis in a process called cellular respiration, which is vital to life. The net equation for cellular respiration is the exact opposite of that for photosynthesis. Cellular respiration occurs in all living things, in both the autotrophs that create glucose and in heterotrophs, organisms that gain their energy by feeding on other organisms. Geothermal energy also powers Earth systems. A minor energy source is the gravitational pull of the moon, which in conjunction with the sun causes ocean tides. Another significant energy source is geothermal heating emanating from the inside Earth, powered primarily by radioactivity. The Earth itself is a source of power. Hydrothermal vents are areas in the deep ocean from which jets of geothermal heated water emerge. Hydrothermal vent communities utilize chemical energy instead of light energy. Communities of living organisms at these locations depend on bacteria at the base of the food. Chemosynthesis closely resembles the photosynthesis reaction. Geology, the physical basis for environmental science. A good place to begin understanding how our planet functions is right beneath our feet, the rocks, the soil, and the sediments. Understanding the physical nature of our planet also benefits our society. Our planet is dynamic, and this dynamism is what motivates geology, the study of Earth's physical features, processes, and history. Two geologic processes of fundamental importance are plate tectonics and the rock cycle. Earth consists of layers. Most geological processes take place near Earth's surface, but our planet consists of multiple layers. Earth's center is a dense core consisting mostly of iron, solid in the inner core and molten in the outer core. Surrounding the core is a less dense, elastic layer called the mantle. A portion of the upper mantle is called the asthenosphere, consisting especially of soft rock. Above that is the harder rock we know as the lithosphere. The lithosphere includes Earth's crust, a thin layer of rock that covers the surface. The heat from inner Earth rises to the surface and dissipates. A geothermal heat pump can then be used to heat or cool a home. The heat from the inner layers of Earth also drives convection currents that move mantle material. As this material moves, it drags lithospheric plates along the surface. This movement is known as plate tectonics. Our planet's surface consists of about 15 major tectonic plates that move at rates of roughly 2 to 15 centimeters per year. The plates' movement has influenced Earth's climate and life's evolution. There are three types of plate boundaries. The processes that occur at the boundaries between plates have major consequences. A divergent plate boundaries, tectonic plates push apart as magma rises upward toward the surface, creating new lithosphere as it cools. Where two plates meet, they may slip and grind alongside one another, forming a transformed plate boundary, faults or fractures in Earth's crusts. Here we have an example of both the divergent plate boundary, and as we can see, they're moving apart. And we also have an example of a transformed plate boundary as they slip and grind past one another. Convergent plate boundaries, where two plates converge or come together, can give rise to different outcomes. One plate may slide beneath another in a process called subduction. When two plates of continental lithosphere meet, the continental crust on both sides might resist subduction and instead crush together, bending, buckling, and deforming layers of rock from both plates in continental collision. Here we have an example of both convergent plate boundaries. We have the subduction on the left and the continental collision on the right. Tectonics produces Earth's landforms. Tectonic movements build mountains, shape the geography of oceans, islands, and continents, and give rise to earthquakes and volcanoes. The topography created by tectonic processes in turn shapes climate by altering patterns of rainfall, wind, ocean currents, and heating and cooling, all of which affect rates of weathering and erosion and the ability of plants and animals to inhabit different regions. Only in the last several decades have scientists learned about plate tectonics. This environmental system of such fundamental importance was completely unknown to humanity just half a century ago. The rock cycle alters rock. Over geological time, rocks and the minerals that comprise them are heated, melted, cooled, broken down, and reassembled in a very slow process called the rock cycle. A rock is any solid aggregation of minerals. A mineral is any natural occurring solid element of inorganic compound with a crystal structure, a specific chemical composition, and distinct physical properties. Here we have a very expertly illustrated picture of the rock cycle. Igneous rock. If magma is released through the lithosphere, it may flow or splatter across Earth's surface as lava. Rock that forms when lava cools is called igneous rock. Igneous rock comes in two main classes, intrusive and extrusive igneous rock. In intrusive igneous rock, magma cools slowly below Earth's surface, and in extrusive igneous rock, the magma is ejected from a volcano. Another type of rock is sedimentary rock. Through weathering and erosion, particles of rock blown by wind or washed away by water come to rest downhill, downstream, or downwind from their sources, eventually forming sediments. Sedimentary rock is formed as sediments are physically pressed together and as dissolved minerals seep through sediments and act as a kind of glue, binding sediment particles together, or called cementation. The formation of rock through these processes of compaction and cementation is termed lithification. These processes also create the fossils of organisms and the fossil fuels we use as energy. The last type of rock we'll talk about is metamorphic rock. When any type of rock is subjected to great heat and pressure, it may alter its form, becoming metamorphic rock. And here's examples of all types, from intrusive and extrusive igneous rock to sedimentary rock and metamorphic rock. Geologic natural hazards. Plate tectonics give rise to creative forces that shape our planet. Plate boundaries, for example, closely match the Ring of Fire, which contain 90% of Earth's earthquakes and 50% of our volcanoes. Earthquakes result from movement at plate boundaries and faults. Along tectonic plate boundaries and in other places where faults occur, Earth may relieve built-up pressure in fits and starts. Each release of energy causes what we know as an earthquake. To minimize damage from earthquakes, engineers have developed ways to protect buildings from shaking. However, such designs are more expensive to build than conventional designs, so many buildings in poorer nations do not have such protections. Volcanoes arise from rifts, subduction zones, or hot spots. Where molten rock, hot gas, or ash erupt through Earth's surface, a volcano is formed, often creating a mountain over time as cool lava accumulates. Lava may also be emitted at hot spots, localized areas where plugs of molten rock from the mantle erupt through the crust. At some volcanoes, lava flows slowly downhill. At other times, a volcano may let loose large amounts of ash and cinder in a sudden explosion. Sometimes a volcano can unleash a pyroclastic flow, a fast-moving cloud of toxic gas, ash, and rock fragments that race down the slopes at speeds up to 450 miles per hour, enveloping everything in its path. Besides affecting people, volcanic eruptions exert environmental impacts. One of the Earth's largest volcanoes, so large it is called a supervolcano, lies in the United States. Landslides are a form of mass wasting. A landslide occurs when large amounts of rock or soil collapse and flow downhill. Landslides are a severe and sudden manifestation of mass wasting, the downslope movement of soil and rock due to gravity. Most often, mass wasting erodes unstable hillsides, damaging property one structure at a time. Occasionally, mass wasting events can be colossal and deadly. Mudslides caused when volcanic eruptions melt snow and send large volumes of destabilized mud racing downhill are called lahars, and these are particularly dangerous. Tsunamis can follow earthquakes, volcanoes, or landslides. Earthquakes, volcanic eruptions, and large coastal landslides can all displace huge volumes of ocean water instantaneously and trigger a tsunami. Residents of the United States are vulnerable to tsunamis as well. One of the best protections against tsunamis is advanced warning. We can worsen or mitigate the impacts of natural hazards. Flooding, coastal erosion, wildfire, tornadoes, and hurricanes are all natural hazards whose impacts can be worsened by the choices that we make. As the population grows, more people live in areas susceptible to natural disasters. Many of us choose to live in areas that we deem attractive, but that are also prone to these hazards. we use and engineer landscapes in a way that can increase the frequency or severity of natural hazards. As we change Earth's climates by emitting greenhouse gases, we alter patterns of precipitation, increasing risk of drought, fire, flooding, and mudslides. Rising sea levels increase coastal erosion. We can reduce or mitigate the impacts of hazards through the thoughtful use of technology, engineering, and policy, informed by a solid understanding of geology and ecology. In conclusion, physical phenomena are in some way tied to nearly every significant process in environmental science. An understanding of matter is essential for all science. Likewise, an understanding of energy is both of fundamental and scientific importance and of considerable practical relevance. Physical processes of geology, such as plate tectonics and the rock cycle, are centrally important because they shape Earth's terrain and form the foundation for living systems that overlie the landscape.